Lesson 9-1, exponential functions. We're going to work on graphing exponential functions and then also the second part, solving exponential equations and inequalities. So an exponential function means that the variable is in the exponent. Here's the general form of your equation. Y equals ab to the power of x. There are a few restrictions on this function. The first one is that a cannot be 0. If you have an a value of 0, then the whole function is 0, and basically what you're graphing is a constant function. So a cannot be 0. B has to be greater than 0. Basically, b has to be positive. And for the reason, that is so that our base is positive when we raise it to a power. We don't want a negative base because then for the even powers, we would get a positive number, but for the odd powers, you would end up getting a negative number, and it would alternate between positive and negative. And then b can also not be equal to 1. If b is 1, you'd have a base of 1. 1 to any power would stay 1. And so the exponent wouldn't really matter here, and you again would have a constant function. So these are your 3 restrictions. Just keep those in mind. 3 facts about these functions is that the domain is always all reals. The x-axis is a horizontal asymptote, and the y-intercept is a. That's an important fact, and we're going to use that later in an example. The y-intercept is this a value here. So let's sketch the graph of this function, and then we're going to state the function's domain and range. You can definitely type this into your graphing calculator, but I'm going to show you how to graph it by hand using a table of x and y values. So our function is y equals 2 to the power of x. And I'm just going to pick 5 standard x values here to plug in. I'm going to plug in -2, -1, 0, 1, and 2. So 2 to the negative second power gives me 1/4 or 0.25. 2 to the negative first power gives me 1/2 or 0.5. Anything to the 0 power is 1. 2 to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. So now we have 5 solid points here that we can graph. I'm going to start with -2.25. -1, 1/2. 0, 1, there's your y-intercept. 1, 2, and 2, 4. So this is what we get here. We get this curve. To the right, it's going to shoot up pretty quickly because it's exponential. And to the left, it's going to approach 0, never quite crossing the x-axis, but getting very close to 0. This is your horizontal asymptote here at 0. So it's going to get very close to 0. These decimals will get smaller and smaller and smaller, but we're never going to reach 0. Okay, so now your domain and range. The domain is always all reals. We can write it as -infinity to +infinity. The range now describes your y values, and the range on this graph, the y values start at 0, not including 0, and they go up to infinity. So we're going to use a parenthesis around 0 because we're never going to hit 0, but it's going to approach 0, and then we're going to positive infinity in this case. Let me show you one more graph here. This time we have 1/2 to the power of x, and I'm going to graph it again making a table, but you could certainly use your graphing calculator to get these points as well. So now 1/2 is our base. If I take 1/2 to the negative second power, that's the same as 2 squared, and so we get 4. 1/2 to the negative first power gives me 2. 1/2 to the 0 power is 1, because anything to the 0 power is 1. 1/2 to the first is 0.5 or 1/2, and 1/2 squared is 1/4, 1/4 or 0.25. Okay, so what happens with this graph here? Basically, it's the mirror image of the last graph we made. It's flipped over, it's flipped around. That makes sense because instead of graphing 2 to the power of x, I'm graphing 1/2 to the power of x. So this time to the left, when x gets negative, we're shooting up. And to the right, for our positive x values, we're getting closer and closer to 0, but never quite crossing the x-axis. This is your horizontal asymptote. So domain and range are going to stay the same for this function. Our domain is all reals, -infinity to +infinity. And our range, again, is starting at 0 and going to infinity, but we're not including 0, so use a parenthesis. 0 to infinity. So I've just shown you 2 examples here. The first one was an example of exponential growth. All of these graphs are going to kind of look like this, where they shoot up as we go to the right. You get exponential growth when the base is greater than 1, like 2 to the power of x. The second graph we made was an example of exponential decay. Here's the general picture of the graph. They're going to be decreasing from left to right. This happens when the base is between 0 and 1. Now, when I say it's a fraction, I'm talking about a fraction between 0 and 1. Not all fractions are between 0 and 1. Like if your fraction is 5 halves, that's not going to be exponential decay. I can't remember what I was saying anymore. Okay, so an example of exponential decay would be like the one that we just graphed, 1/2 to the power of x. Okay, so example 2, we need to determine whether each function represents exponential growth or exponential decay. All you need to do here is look at the base. So in example A, you have 2 times 5 to the power of x. The base here is 5. Because it's bigger than 1, this is an example of exponential growth. And letter B, you've got 2/3 to the power of x. Because the base is a fraction and it's less than 1, you've got exponential decay. Okay, so let's switch it up here. In example 3, we're going to write an exponential function for the graph that passes through the 2 points 0, 3, and 1, 15. What you need to do here is use the general form of our exponential function, and that's y equals ab to the power of x. With these 2 points here, we really have 3 values. The point 0, 3 represents your y-intercept. And we know back from our definition that the y-intercept in this function is a. So you can plug in 3 for a. Now from this point 115, it's 1 point on the graph here. It gives you an x and a y value that you can plug into your function. So the y value is 15. The x value is 1. What we don't know is the base. We don't know b, and so that's what we need to figure out. So I'm going to divide each side by 3, and I get 15 over 3. That's 5 equals b to the first power, so 5 equals b. Now we can write the function, the general equation. You're going to write y equals 3 times 5 to the power of x. 3 is your y-intercept, 5 is your base. There's your function. Okay, the last part of this lesson is solving equations and inequalities where you've got the variable and the exponent. So solving this equation here, I need to figure out the value of n that makes this equation true. The easiest way to do this is get the same base on both sides. Okay, so I'm going to make a note to the side here. Get like bases. So the power sheet that we used back in chapter 7 and in chapter 8 is going to be helpful here. I want to rewrite the right side of this equation, 81, using a base of 3. And if you use your power sheet, 81 is the same as 3 to the 4th power. So I'm going to change the equation so that I'm using a base of 3 on both sides. If you get the bases to match, we know that their powers have to be equal. So 3 to the 2n plus 1 equals 3 to the 4th power. Well then 2n plus 1 has to equal 4. The powers have to be the same on both sides. So we can easily solve this for n. 2n equals 3. Divide each side by 2, n equals 3 halves or 1.5. Now if you wanted to check it, you could plug it in. 2 times 3 over 2 plus 1 gives you 4. So 3 to the 4th power equals 81. Yes, it checks. Here's another equation. 4 to the 2x power equals 8 to the x minus 1. Again, we're going to be able to get like bases here. Think about how you can rewrite 4 or rewrite 8 using exponents. Both of them can be rewritten using a base of 2. So 4 is the same as 2 squared. So I'm going to change 4 into 2 squared. But then that's to the 2x power. Equals, on the other side, 8 can be rewritten as 2 to the 3rd power. 2 cubed is 8, so you have 2 to the 3rd, but then it's to the x minus 1. Okay, now using properties of exponents, when you take a power to another power, like we have here, the rule is to multiply them. So we're going to keep the same base of 2, but I can multiply these powers and simplify the equation. 2 times 2x is 4x. And on the right side, I've got a base of 2, and if I distribute the 3 here, you have a power of 3x minus 3. We're going to multiply the exponents, so we need to distribute 3x minus 3. Okay, now we're set up to solve the equation. Both of them have a base of 2, so you can set the powers equal. 4x has to equal 3x minus 3. And if we take away 3x on each side, we get our answer, x equals -3. Okay? These are pretty fun to solve, but you do need to get a like base on each side, so using that power sheet that we were using in class can actually be really helpful in this chapter too. Okay, last, letter C, I'm actually going to have you try this one on your own because I want to move on to the inequalities. Okay, so moving on to example 5. Solve each inequality. Well, again, we need to get a like base on each side, so because I have a base of 4 over here, I'm going to try to get a base of 4 over here. And if I can't, maybe I can get a base of 2. Just depends here. So I'm using my power sheet here, and I'm looking in the powers of 4. 256 is actually 4 to the 4th power. So 256 is 4 to the 4th, but it doesn't really help me here. I want to rewrite it using a base of 4, and I've got 1/4 to the 4th. Anytime you've got this fraction here, what it really means is you're using a negative exponent. So we have 4 to the 3p minus 1 is greater than, instead of saying 1/4 to the 4th power, we need to write it as 4 to the -4th. Let's think about that here. If you have 1 over 4 to the 4th, you can rewrite it as 4 to the -4th. That's what I'm doing here. So now I've got the base of 4 on each side, and I can set up my inequality using the powers. 3p minus 1 is greater than -4. We'll add 1 to each side. 3p is greater than -3. Divide each side by 3. And p is greater than -1. Okay? Again, you can check it pretty simply. If you want to plug it in, you can check to see that this side will be greater than 1 over 256. Okay, this is our last example. I'm going to show you one more inequality here, but you basically solve it the same way that you would solve an equation. So on the left, I've got a base of 3, and I can't really reduce that, so I'm going to think about rewriting this right side using a base of 3. Yep. So using my power sheet, I'm going to look up 243. 243. Okay, it's in the powers of 5. It's actually 3 to the 5th power. So 243 is 3 to the 5th power. But since it's in the bottom of my fraction here, I'm going to have to rewrite it as 3 to the -5th. So here's how I'm going to set it up. 3 to the 2x minus 1 is greater than or equal to 3 to the -5th. Because it's a fraction, 1 over 243 or 1 over 3 to the 5th, that's the same as 3 to the -5th. Now we can set up our inequality using the powers. If they have the like bases, now you can use their powers. 2x minus 1 is greater than or equal to -5. I'll add 1 to each side. 2x is greater than or equal to -4. And divide each side by 2. X is greater than or equal to -2. Done. Okay? You definitely could test some points here, check your solutions, but we're good to go with these. There's not going to be any extraneous solutions. Okay, so we're going to work on this assignment in class. Thank you for watching.